Most fuel system leaks occur among the underground pipes. It is not uncommon to hear about underground pipe failures, and the increased regulatory scrutiny of pipe systems has added to this awareness. It's best to spend some time on the underground pipe selection and design. It's much easier to do it right the first time.
Modern fuel systems are always designed with double-wall underground piping, where leaks can be contained and detected. Fiberglass double-wall pipe is the most commonly used underground fuel pipe. It is widely available from local distributors and can be installed with moderate skills and minimal tooling. The pipe is assembled from 20 feet long stock lengths with epoxy adhesive for joints using factory-supplied socket fittings. Straight lengths of the outer containment pipe allow for openings to access the joint locations on the inner pipe. Two-piece containment fittings close off the secondary pipe after testing of the inner primary pipe. Fiberglass pipe benefits are wide availability and acceptance, inherent non-corrosion characteristics, and ready adaptability to site routing requirements. Potential problems are its requirements for a relatively large number of field joints and its higher potential for physical damage versus steel pipe. Steel pipe systems are often used in large commercial, institutional, and military applications. The exterior pipe is typically coated with epoxy or fiberglass to protect against corrosion. However, supplemental corrosion protection is required, typically in the form of anodes. Steel piping systems can be factory assembled with multiple carrier pipes, such as fuel supply and return pipes, within a common containment pipe. The benefit of steel pipe systems is relatively high strength, including welded connections to prevent against physical damage. Drawbacks are the skill level required to fit up and weld the piping, and the relative lack of field adaptability. Double-wall flexible underground piping has had a mixed performance record. The pipe is a co-extruded plastic pipe with a liner designed to resist fuel impregnation. Joints are provided by mechanical clamp fittings or in some system by heat fusion. The benefit of the system is that it can be provided in continuous lengths up to 250 feet, which dramatically reduces the number of field joints subject to leakage. Drawbacks are issues experienced with fuel compatibility, biodegradation, and excessive thermal expansion. It is important to plan pipe routing to enable the future excavation and repair of the pipe. Do not route piping under equipment that would prevent its future access. Another aspect of pipe routing is that it typically needs to slope back to the source tank to allow drainage if needed, and also the low point detection of leaks in the secondary space. The slope may dictate a deeper than normal tank burial depth if the pipe run is long. Adjacent underground utility lines should also be considered to allow for installation and future repair of pipelines without the potential of damage to other utility systems. Mission-critical applications would typically allow for independent and redundant pipe routing from the tank to the building wall. It is important that these lines be provided with some separation to allow maintenance or repair without the threat of damage to the redundant pipeline. Underground pipelines are subject to stress from surface loads, settlement, freeze-thaw ground movements, thermal expansion and contraction, and damage from adjacent construction. So problems can occur requiring repair or replacement. A second source of problem is where pipelines enter underground sumps at tanks or transitions to above ground or in-building piping. The pipe system may be okay, but need to be shut down for repair or replacement of the sump seals. Inspection and test requirements for underground fuel piping have been becoming more stringent as environmental protection regulations develop. Any failed test may require that the pipeline be removed from service, so the need for redundant piping runs underground is increasingly important. The most common method of leak monitoring for underground double-wall pipe is by a leak detection sensor located at the low point of the pipe run, usually within a containment sump. Recent regulations in California have required a positive means of assuring containment rather than the passive low-point sensor method. The vacuum method generates a vacuum within the pipe interstitial space and measures the vacuum decay rate to determine integrity. The vacuum may be generated by a submersible pump adapter or a dedicated vacuum pump. Another California-approved positive method is hydrostatic. Hydrostatic leak detection uses a liquid within the interstitial space of a tank, sump, or pipe. A level sensor is used to monitor for a change in liquid level that would indicate a leak. This method has been proven for several decades monitoring underground fiberglass tanks and is commonly used for underground sumps. Continuous cable leak sensors are used in long pipelines, typically with pre-engineered pipe systems. The cable has the benefit of being able to locate the source of the leak within the pipe. Drawbacks are the higher initial cost and potentially increased maintenance. Submersible pumps have a standard accessory item that is a mechanical leak sensor. When the pump starts, the device is sensitive to a drop in pressure that would indicate a leak. When that leak is sensed, the device automatically closes to restrict flow. The devices are commonly used in service station applications, but are considered less reliable for mission-critical applications. Veeder-Root and other tank management panels have optional electronic line leak detectors. The test operates while the system is not otherwise in use to start the submersible pumps momentarily and build pressure in the line. A pressure transducer in the pipeline measures any pressure loss that would indicate a leak. Underground piping details and transitions to above-ground or in-building pipe systems can be a source of problems. Part of the issue is that above-ground and in-building pipe is typically steel, while underground pipe is non-metallic. Another aspect is the potential for differential settlement that must be accommodated. Transition sumps are typically fiberglass or HDPE and may be single wall or double wall. The piping systems enter the sumps through watertight fittings. Valves are commonly located within the sumps to isolate the piping sections for testing and repair. Leak sensors are included in the piping sump. Manufacturers Bravo and Western Fiberglass, amongst others, have some good details on transition sumps.